Question 7 is just a reminder that infrared spectroscopy particularly is used in all kinds of situations, not just in the chemistry laboratory, and you just need to know a couple of examples of applications of that. So environmental monitoring is quite an important one. If a molecule has a very characteristic infrared absorbance, you can use the intensity of that absorbance in a sample as just a measure of the concentration of something. So it's used, for example, for measuring carbon monoxide levels in air samples, because obviously that's an important safety hazard that you need to be constantly monitoring for in situations where it's likely to be a problem. Likewise, you can detect hydrocarbon levels in air in the same way. And the other sort of famous thing is that you can monitor the concentration of ethanol on your breath by using a characteristic absorption band from the ethanol spectrum, and that's the way breathalyzers work. So it's just being aware of those things. You don't need any details, but you do need to know the examples. In question 8 then, we have the information that this compound that gives these spectra contains carbon, hydrogen and oxygen only. And based only on that information and the infrared and mass spec, we have to propose a structure for the compound. So if we start with the infrared and we do the usual things, we look for the characteristic peaks, then the first thing to leap out at you may well be this thing. Strong peak in between 1500 and 2000. You're going to think that looks like it could be a carbonyl peak, but as always you check. You don't just say, oh, that looks like it's roughly in the right place. You check. So you say, right, should be, if it's C double bond O, it should be 1630 to 1820. So you put your marker on at 1820 and you find, yeah, it's somewhere like that, and you put your marker on at 1630 and you find, it's somewhere like that. So yeah, that fits. The peak is nicely within that window. So you say, right, the compound contains C double bond O, and when you're writing your answer down, it's important you explain how you know it. Don't just say infrared shows it contains a carbonyl group, because they need to know how you know that. They need to know you didn't guess. So you say peak at 1630 to 1820 wave numbers. Okay, it's really important to back up your assertions like that when you're talking about spectra. Then you go looking for OHs. You can see it's not a carboxylic acid because you don't have that big broad 2500 to 3300 peak, which would be sort of here. But what you do have is this, and that looks absolutely like an alcohol OH. But again, you check. So it should be, if that's going to be an alcohol OH, as opposed to a carboxylic acid one, your data sheet tells you 3200 to 3600. So again, you mark on 3200 and you say, yeah, that looks good. 3600 is sort of here. And so again, you say, yeah, that fits well. So check the peak is actually in the right place, and then you say yes. Okay, so we can add that to what we know, that it contains an alcohol OH, and again list the position, peak at 3200 to 3600 wave numbers. Okay, and that's all we get from the infrared. That's a CH, but that's not interesting. That's the fingerprint region. We can't interpret that. So that's what we know from the infrared. So then we come to the mass spec. And the first thing we look at is the molecular ion peak, which, remember, is the peak furthest to the right, accepting the possibility that there might be a small carbon-13 satellite peak, which you can actually see in the spectrum at 75 in the actual spectrum, but that's due to C13. So 74 is the molecular ion peak. So you identify that and you explain. Don't just say the molecular ion peak shows the MR is 74, because they'll say, how does it show you that? So you say that the molecular ion peak has M over Z is 74, and you explain that this means that the MR is equal to 74. Okay, you've really got to spell it out. So, at this point, it's a good idea to see if we can come up with a likely molecular formula before we get stuck into the most difficult part, which is trying to figure out about fragment ions. So, we know from the infrared that there must be at least 2 oxygens in the molecule. Okay, because one of them's in a carbonyl group, one of them's in an OH group, so those have to be 2 different oxygens. There could be more than 2. The infrared doesn't tell you how many OHs and how many carbonyls, but you know, always start with the simplest assumption. So if we say, right, that we've got at least 2 oxygens based on the infrared, so 2 lots of 16 equals 32. And if we take that from the total MR, so the MR is 74, and 74 minus 32 is equal to 42, is the MR of the rest of the molecule. So if we work on the assumption that that doesn't contain any more oxygens, or it could be wrong, but let's go with that. And think, well, what would that mean? How many carbons could that be? Well, if it was only 2, that would add up to 24, and that would give you a gap of 18. So you'd have C2H18, and that's not possible. It's far too many hydrogens to fit around 2 carbons. 3 carbons, on the other hand, takes you to 36. So you'd have C3H6 for the rest of the molecule. That looks fine. C4 is too many because 4 12s are 48, so that's already too much. So that suggests that C3H6O2 is the likely formula. We can't say for sure that that's the case because, as I say, we can't rule out the possibility that there's a 3rd oxygen in there. But let's go with that because that's the simplest thing. So C3H6O2 containing a carbonyl group, but also containing an alcohol group, not a carboxylic acid, so they can't be joined together to make a carboxylic acid group. So let's explore the possibilities, because it's only a small molecule, so there aren't that many different ways that we can do that. Okay, so this is what we know from what we've done so far. And so we just think, right, what could the structures possibly be? So if we've only got 3 carbons, let's stick those down first of all and think, right, we've got to put a carbonyl group on there. So 2 possibilities. Carbonyl group could be on the end. This end or that end makes no difference. So we could have an aldehyde like that, or it could be in the middle. Then we've got to put an OH group on as well. For this one, there's only one way we can do that, because the OH has got to be there or there, but whichever of those 2 it goes to, it's the same thing because of the symmetry. So that would be one of the compounds. And if you add that up, you've got 3 hydrogens there, 2 there, 1 there, makes 6. So that does fit C3H6O2. For this one, there are 2 possible ways of putting the OH on, because it could be here, or it could be there. Okay, so those are the 3 candidate structures. Not this one, because that would give the characteristic carboxylic acid OH peak, which we don't have, so not that one. So then we have to think, right, well, how can we tell? Can't tell from the infrared, but we can potentially tell from the fragments in the mass spectrum. So these are the peaks we got to work with. That was the molecular ion peak, remember, so it's these 3, 31, 43 and 45, and we've got to look for fragments of those, and if any one of those compounds is right, it should really account for all 3 fragment peaks. So if we start with this one, if it broke here, which is possible, okay, single bond, so if it broke there when it was a molecular ion, you could get 2 possible fragment ions. Remember, you don't know which one you'll get, you might even get both, because it depends on how sort of random the splitting is. So you just don't worry about that, you just look at all the possibilities. So you say, right, if we got OH plus, that would give an M over Z of 17. And if we got the rest of this, then we can just take 17 away from 74 and realise that we'd get 57. So that's not any of these peaks, but that doesn't necessarily mean anything. The fact that you don't see those peaks doesn't matter, because it may just be that that fragmentation doesn't tend to happen. So you can't rule the structure out because these peaks are not there. That's important. Okay, it's not like infrared, where if you haven't got a peak around 1700 wave numbers, you know for sure there's not a carbonyl. You can't do that with mass spec. So the fact that we haven't got those fragments, that means nothing. So what about if it breaks here? So this time we would get potentially CH2 OH plus. So OH is 17, CH2 is 14, so that would come to 31. And that's exciting now, because that's one of the things that's there in the molecule. So we could explain the 31 peak from that one. The other fragment that you'd get from that would be the CH3CO peak, and that comes to 43. So that's exciting as well. So 2 of the fragment peaks can be explained from that structure. The problem is that you can't explain the 45 peak, because if you split there, you'd get 15 if you got CH3 plus, or if you take 15 away from 74, you get 59, and neither of those is 45. So that structure almost makes it. You almost think, yeah, that can explain everything, except it can't explain the 45 peak. Okay, so we try one of the others and see whether one of the others can explain all 3 of them. So if we try here, again, we know that taking OH away will do the same thing. It'll make 17 and 57. So there's no point worrying about that, or indeed about that, because we know that if you take 17 away from 74, which is the total M over Z for all of them, we're going to get 17 and 57, which doesn't help us. So let's ignore that. Again, we know what's going to happen here, because that's just breaking CH3 off, same as we did there. So that's going to give us 15 and 59. So again, that doesn't help us. What about if you break here? Well, that's going to give us CHO plus, which is 29, would be a possible peak we could get from there, but that doesn't help us. And if we take 29 away from 74, we get 45. So we could get the 45 peak, which was the one we couldn't get before. So that structure could give you the 45 peak, but not the 31 and 43. So again, it doesn't work. It gives you one of the peaks, but it doesn't give you the other 2. So we have to hope that this one will give us all of them, otherwise we're in trouble. So again, we ignore that one because we know that's not going to do it. But what about if we break here? Well, that could give us CH2OH plus, which weighs in at 31. So that's good, because that's one of the peaks we need to account for. And that leaves behind 43. So depending on which side the positive charge goes on, if it goes on that side, the CH2OH plus, you get the 31 peak. If sometimes in some other molecules it goes the other way and it goes on this side, and you get the CH2CHO peak, you get 43. So both of those are possibilities. So now comes the big moment. If we break it here, what do we get? Well, we're breaking off the aldehyde again, so that would give us 29 for CHO plus, which doesn't help us, but what it leaves behind is CH2CH2OH, and that adds up to 45. So that fragmentation, if it just broke there and left CH2CH2OH plus, that would come to 45. So that gives us all 3 fragments. Okay, and that therefore is likely to be the correct structure, because it's the only one of the three which gives us all three of the fragments. So that's an example of mass spec at its best, where you can actually solve a real problem just based on the fragment peaks. It doesn't happen very often. When we learn about other kinds of spectroscopy next year, you'll tend to find you don't use fragments all that often, but just sometimes it's really nice because it can pinpoint the right answer, as it does in that case. So that's your answer. When you're explaining it, make sure that you identify each of those fragment peaks. So you need to write them down. Okay, all this working that I've shown there is fine, but as far as an examiner marking it is concerned, they'll just say that that's a load of gibberish. There are just squiggles and numbers all over the place. So you have to say, right, this is the molecule and these are the fragment ions, and you must write them out properly and explain how each one fits. So the 31 is CH2OH plus. Okay, so make sure that's written down, because that's what the mark will be for, is actually identifying the fragment ion. The 43 peak is CH2CHO plus. And the 45 peak is this one, CH2CH2OH plus. Okay, and it's that list of the actual fragment ions, that's what would get you the mark.